Okay, so now I want to talk about um, circular motion and gravitational effects. Uh, the great analogy with this is roller coasters and loops and roller coasters. Um, if you've ever ridden in loops and roller coasters, as you go through the top of the loop, you kind of feel lighter, and sometimes or most times, they design it so that you have a collar around you so that it kind of holds you in. Um, so that as this track goes around, you don't just drop out of here. Um, but you at the bottom of the circle, you kind of feel sucked down into your seat, and that's because gravitational forces are constantly down, but the centripetal force is always directed towards the center of the circle. So, from the perspective of the center of the circle, you're constantly changing where you're at as you go around through this vertical loop. Think we're okay with this force centripetal equals mv squared over r. I've had a chance to practice it a little bit. You'll notice here this little bit of info bit. Roller coaster loops are shaped, use a shape called a clothoid, where the curvature increases at the top. This reduces the speed needed to move safely through the loop, because if you weren't moving fast enough, you could just fall out of this loop. It also adds thrills by having relatively longer vertical parts in the loop. All right, so let's look at some of the physics involved here. Um, at the top of a loop. So in this picture, they're at the top of the loop. And if you think of the forces that are directed towards the center at the top of the loop, there's an applied force, or in this case, they call it a force normal here, but it's the ride applying a force on you to keep you in circular motion. If that ride wasn't there, there wouldn't be any force being applied to that direction. But gravity is also down. And so the ride applying the structure of the ride applying a force on you and a gravitational force are both down towards the center at the top of the loop. So if you're moving fastly through the loop, what ends up happening is that if there was it's like it says here, the first time through the loop, the speed is such that the roller coaster experiences a 1,500 Newton force to keep it moving in circular paths. At the top of the loop, the roller coaster will experience a centripetal force that is the sum of the force gravity and the force exerted by the track. So if you're traveling fast enough that you need a 1,500 Newton force, and the gravitational force is 1,000 newtons, that means the ride has to apply a 500 Newton force to keep you in circular motion. So then you just go flying straight off here like that. On the other hand, you could be traveling just fast enough so that the centripetal force needed to keep you in circular motion is 1,000 newtons. And because your weight is 1,000 newtons, then at this point up here, the only thing that's keeping you in circular motion is your weight, which is if you're on the ride at this point, you'd feel weightless for a second. You wouldn't really be falling, but you wouldn't have, you just be kind of hovering on your seat because your gravitational force is the force that's keeping you in circular motion. And that's at a minimum speed to make it through the top of the loop. On the other hand, if you're going too slow, then the centripetal force isn't even big enough to match the gravitational force. And what ends up happening is that potentially people could fall on the loop. Um, and so, the design of a roller coaster the designer of a roller coaster has to be aware of some of these forces involved and ensuring that the ride itself is safe. So here's an example. A 700-kilogram roller coaster full of people goes around a vertical loop that has a diameter of 50 meters. What minimum speed must the roller coaster have at the top of the loop to stay on the track? Well, the minimum speed that's needed is if the centripetal force, the circular force needed, is matched by the gravitational force. That's the only force keeping you on, is the gravitational force. So that's how you do these minimum speed questions. So you'd say mv squared over r equals mg. You get v squared over r is equal to g. V is equal to the square root of the radius times the gravitational field strength. Or the radius is 25 meters times 9.81 square rooted, and you'd have to be traveling 15.7 meters per second at the top of that loop. Otherwise, the roller coaster would potentially fall. Now, clearly, they don't design roller coasters so they'll just fall. They have wheels on this side too to hold it just in case there's a speed problem so it doesn't just fall. But if those special wheels weren't designed to ride on the top and bottom of the track like this to hold you on, then potentially that would be an issue where you'd fall. Place where this happens, it's kind of fun, especially in nice weather. I usually go outside and do this sometime in May with my class. Kind of miss the opportunity to do that, but spinning a bucket of water. Okay, if you spin a bucket of water and you spin it just fast enough, you don't need to apply any force to keep the water in there. But if you spin it too slow, as it's coming up here, the water will fall out on top of you. And so it's kind of fun little experiment where you kind of take your bucket and you spin it. You got to have a pretty good handle so it doesn't break. That usually happens. Sometimes it breaks and the bucket goes flying off. But if the handle's good, you can spin it just fast enough so the water stays in, even though it turns upside down on you. And that's like this minimum speed type question, where the force centripetal is matched by force gravity. If you move it faster, then there has to be another force, a tension force, that is keeping it going in circular motion. On the sides of this circular motion, what ends up happening is that the only centripetal force you have is the tension force in your handle. Gravity does not affect the centripetal force when the bucket's on the side. And then at the bottom, then all of a sudden, the force centripetal is going to be the force tension acting up, subtracting the force gravity down at the bottom. This is a vector equation. I don't really like how they wrote that. I would have wrote it as force centripetal is equal to the applied force or tension force minus the force gravity. You'll notice that on your formula sheet at the bottom of your circular motion. Because of that, when you're spinning something in circular motion on the bottom part of the loop, that's when it feels the heaviest or the most force is needed. So this question says a bucket of water has a mass of 1.5 kilograms, spun in a vertical circle. The radius of the circle is 0.75 meters, and the speed of the bucket is 3 meters per second. What's the tension on the rope at position C, which is the bottom of the rotation? So when we're going to figure that out, we would say the force centripetal is going to equal the force tension minus the force gravity. I don't really like how they've rearranged their formula here, but what I'd probably do with this one, instead of doing this, I would have force tension minus force gravity here. I'd still have my mv squared over r, but because I have tension minus force gravity, basically I'm going to take my centripetal force and add the force gravity to the other side. They got a minus here. That's how they add it over. So if you're looking for the applied force, like I said, tension minus force gravity, you would just add the force gravity over to the other side, and it would give you the tension force.